Okay, so when I say a decimal number system, this number system is having total number of 10 digits. Okay, whereas it is having numbers from 0 to 9, total 10 digits. Then whenever a number is being written, and to denote it as a decimal number, we need to write a base as 10. So when I write base as 10, then that number will be considered as a decimal number, right? This is as usual we use in our daily lives. Okay, then when I say octal number system, octal is 8, right? Whose base is going to be 8. So any number, if it is written and the base is written as 8, that number is considered as octal number system. Okay, say for an example, I'm going to write here 556.7 something, or 5567 with base is 8. Okay, so the base here for this number, the base is 8. So what will happen? This 5567 will be considered as octal numbers. Okay, which consists of 0 to 7 numbers. That is total of 8 digits. Then base 5, where for an example, if the base is 5, the number is considered as some which is having 0 to 4 numbers, for an example, right? But we don't have that number system. Then base is 16, which is called as hexadecimal number system. If a number is having base 16, then that number is considered as hexadecimal number. Okay, and that consists of the numbers from 0 to f. Okay, after 9 we don't have any number. In decimal also we don't have any number. So hexadecimal is decimal plus hex 16. So it is going to be a, the 10 in decimal is considered as a, is being written as a in hexadecimal number. So we are going to denote one extra symbol for number 10, a, then it goes on b, c, d, e, f. So f is going to be 15, that is 0 to f. So total number of 16 digits, which is a hexadecimal number. Then usually, as usual, base 2. So any number that is 0 and 1, only two numbers will be present in this base system, base 2 system, 0 and 1. So if I want to go further, then we need to combine, we need to join two numbers, and that is what a different configuration of combinations of binary numbers we will get. So with a simple table here, we can come across this as, okay, so let us consider this table, whereas the decimal is there, octal number system is there, hexadecimal is there, as well as binary number system is there. Okay, so what is happening here? 0 is present in many, in all other number system also, right? So 0, 0, 0, and in binary number system it is also 0. Okay, then the 1 in decimal is same one in octal, in hexadecimal again it is same, in binary again it is same, 1, 0 and 1. Now to determine only two digits, 0 and 1, in binary system I have same as 0 and 1. Now when I go for 2 in a decimal number, if I say 2, then The octal number is also consisting of a number 2. Then in hexadecimal again it is same 2. But when I go for binary number system, I don't have 2. Then I will combine two digits as 1 0. If I write 0 1, you know what will happen? It is considered as 1 only. So now I'll go for 1 0. So I'm joining two bits. Okay. Then if I go for 3, the 3 what I can write as 1 and 1. Okay, 1 and 1. Suppose if I want to convert this into some decimal or octal number, see 1, how this is going to be converted. That is why I told you to watch the lecture 3 and lecture 4 from 18EC 34. I hope you have seen it. I'll just uh, bypass some other examples with only one basic example. Okay, so if I want to convert this 1 and 1, how this is going to be 3, how this 1 is going 1 1 is going to be 3. So it is going to be converted as 1 into 2 raised to 1 plus 1 into 2 raised to 0, which is equal to 2 raised to 1 is 2, 2 into 1 is 2, plus 2 raised to 0 is 1, and 1 into 1 is 1. So 2 plus 1 is 3. Okay, so this is what the number. When I combine these two numbers, it will give me the number 3 in other system. So for an example, if I take 1 0, see 1 into 2 raised to 1 plus 0 into 2 raised to 0. Whereas 2 raised to 1 is 2, 2 into 1 is 2. 2 plus 2 raised to 0 is 1, 1 into 0 is 0. So 2 plus 0 is 2 only. Okay, so that is the combination of 1 and 0. Likewise, every other bits I'm going to get it as. So when I go for 4, now what I will do, I'll take it as 1 0 0. Now one bit has been increased. I'm just considering this number 2 and then one more 0, 1 0 0. Okay, then by keeping these left two bits as same, I'll just change the bit, the LSB, least significant bit. So now what I will get, 1 0 1. Now least significant bit has been done. 0 once it came 0 and once it came 1. Now I will move on to the middle bit. So now here 1 0 1, I'll keep this 1 as same MSB. Then the middle bit I'm going to change it as 1. Now again the LSB is going to be 0. Now again what here, 1 as it is, then again 1 as it is, the LSB is going to be 1. So one time it is going to be 0, another time it is going to be 1. Likewise 0 1 0 1 0 1 0 1, it goes on. Okay, say after 7 in decimal number system, what I will get, 8, right? Then in octal number system, I don't have any number rather than 0 to 7. Then I am going to combine this 1 and 0 as I did in binary number system. I am repeating these numbers 0 to 7 only. So after 7, what I will get, 1 0. So base is always 8. But in hexadecimal number, I have that number, so I will write directly as 8. Okay. Whereas here, all these 3 bits are done now. Okay. So what I will write is 1 0 0 0. So these three bits are made 0 0 0, and one extra bit has been taken. okay, combined with these 3 bits. So that will give me the output of 8 if I convert this into some hexadecimal or some decimal number. Okay, so like 1 is there, 1 into 2 raised to how many positions? 0, 1, 2, 3. 2 raised to 3 plus 0 into anything is 0 plus 0 into anything is 0 plus 0 into anything is 0. So 2 raised to 3 is 2 raised to 3. 2 into 2, 4. 4 into 2, 8. Right? 8 into 1 is 8. So 1,000,000 will give me the value 8. Okay. Then, so it goes on like that. Here 9 is 1,001. Then after 9, we don't have other number in decimal number system. So it will be 10. After 9 it will be a 10 in decimal number system, but in octal number system it is going to be changed. Okay, the 10 or the 10 in decimal number system is represented as 12 in octal number system and a in hexadecimal number system, and here it is just a combination of number of uh, binary digits 1010. If I convert this 1010, I will get a or 10. Then it goes on 11. Here it is 13. Here it is B, and here it is 1011. Say 12, 10, sorry, double one, double zero. D, double one, zero, one, and E, triple one, zero, and F is 1111. Okay, so this is how it goes on. Then after F, I don't have other number in hexadecimal number system. So 15 in decimal number system, 17 in octal number system, F in hexadecimal number system, 1111 in uh, binary number system. Okay, so after this, after 15, what will come in decimal? It is 16 as usual, right? Then after 17, I don't have other number. 7 has been came now. After 7, I don't have any other number. So this first digit will be changed to 2. So in octal number system, after 17, 20 will come because 8 and 9 is not there. Only 0 to 7. Okay, 20 is represented as 16 in decimal number system. And after F, now again I don't have any number in hexadecimal number. So what I will do, I'll just combine the two digits, that is 1 and 0. So for 16 in decimal, I will get 10 in hexadecimal. And the same thing, now 4 digits have been completed. Different combinations of 4 digits, 4 bits binary number has been done. So here what I will get is one more extra bit plus 0000. These 4 bits are made 0000 and one extra bit has been combined. So to notify, to denote more than 16 numbers, I require 5 bits, right? So it is like that. Then it goes on like that. Again, starting from here, 17, here it is after 20, 21, here it is 10 to 11, and here it is 1, 0, 0, 0, 1. Now here 1, 0, 0, 0, 1, 0, 2, 1, 0, 0, 1, 1, 3, that is 19. Then 1, 0, 0, sorry, 1, 0, 0, 1, 0, 1, 0, 1, 5. This is same as where I have got the numbers here. 100 is 4, so that is 4, this is 5, but these numbers are going to be changed. MSB. Okay. So to easily write everything, I'll combine 4 bits here. 0001 is nothing but 0001. 1 only. 00. That's it. Okay. Just repeating all these numbers. 1 to 7. So that is all about a number system and a conversion of number systems. So to move on to a second module, that is a conversion of number system. To move on to a second module, we should know what is actually a combinational logic circuit. Okay, so basically it is a type of digital logics, right? That is a number system logics, which is implemented by using a Boolean circuit. So when I say Boolean circuit, that circuit is going to provide me a Boolean functions. That in the previous class we have discussed about Boolean functions and Boolean rules. Okay, so to implement any Boolean circuit, a combinational logic circuits which are using a digital logics that are being implemented. Okay, whereas the output is pure function of present input only. This is most important. So whenever I go for combinational logic circuits, the output is completely depending upon the present input. You may ask, what is a present input? Now, say when I say present input, a current state of the input, and this Boolean function, Boolean circuits are going to work upon a binary number system. Okay, so whatever the input right now is given, the output is going to depend on that, because these circuits may have a memory. So in a memory, what will happen? There may be a previous data, there may be a future data, whatever it may be. But in this combinational logic circuits, always the output is depending upon the present input. Okay, present input. That is very much important. You should know about combinational logic circuit. There is another type of digital circuit, that is sequential logic circuits, whereas the output is depending upon the present input as well as the previous input. Okay, so when I say combinational logic circuits are made up of basic NAND, NOR, NOT, and OR gates. Okay, that are combined together to connect to produce uh, switching circuits. That is, okay, for an example, we have a NOT gate, we have an AND gate, then we have OR gate. So by using these basic gates, AND, OR, NOT, and we have a NAND. NAND is combination of AND as well as and NOT. So NOR and NOT gates. These are main basic building blocks of any digital systems. Okay. So here many multiple inputs and output is depending upon the function of input. What type of function that we are going to use, and those functions are AND or NAND. Yes. Someone raised a hand. Do you have any doubts? Okay, no doubts. Fine. So here, combinational logic circuits, the input, multiple inputs or single input for a NOT gate, that is a function of, the output is a function of a pure input, present input. Okay. Say when I say for an example, AND gate. So what is a function of AND gate? There are multiple inputs, there is a single output. So what is the function of this AND gate? It is a dot matrix, a dot, that is a product term, to produce a product term of the inputs. So the function of this is A dot B. So F equal to, or C is equal to A dot B. So this is the function. So C is completely depending upon the A and B, present input of A and B. Okay, so here A is input, B is input. Okay, AND function is there and NOT function is there. NOT function is having only a single input. A is input or anything input. If I produce this, if I connect a NOT gate here for the output of AND gate, then here C is equals to A dot B whole bar, correct? A dot B is the output of AND gate, and then give it to the NOT function, then output will be A dot B whole bar. Okay, so this is A dot B whole bar, and this is A dot B. This is AND, this is NOT. So 0 into 0 is 0, 0 into 1, 0 into 0 is again 0. Here 1 into 0 is 0, and 1 into 1 is again 1. 1 into 1 is 1. So this is given to a NOT gate, whereas 0 is complemented and it is made as 1, again 1, 1 and 0, right? So the output is completely depending upon the inputs only. Okay. So combinational logic circuits. It is a combination of AND or NAND NOR and NOT gates, which where the output is completely depending upon the present input. Okay, one example is there. So there are three ways to specify the function. What type of function it is going to generate? That is going to have a Boolean algebra. Based upon a Boolean algebra, it can be determined by using a truth table, and it can be determined by using a logic diagram. Okay, so any function we need, that function is a Boolean algebra. Then we need to write a truth table for that, and then we need to draw a logic diagram. Okay, so for this, like this, this forms algebra expressions showing the operation of the logic circuits. Okay, see like this. Now this is an expression. If this is an expression, based upon this expression, I can write the truth table, and then by utilizing this expression, I can draw a logic symbol. Okay, so see for an example, what is a dot b whole bar dot a plus b whole bar dot c, right? So here I am going to use one and NAND gate, which is going to give me a dot b whole bar, right? Then what I require, a plus b whole bar. So I'm going to use NOR gate, or plus not, this one a plus b whole bar, right? And then c I'm going to give as a product. All these are product. So I'm using one more AND gate here, where I'm giving the output of these two gates directly C. So I will get this expression. So from this, I can see what type of output it is going to give me, right? So if I put different number of bit binary combinations, then I can generate this truth table. Okay. If you have not understood this, how it is going to work, I can explain. Anyone can reply. Any doubts in this? It is a simple thing that a combinational logic circuit will be having a three specific functions. One is Boolean algebra or Boolean function. Another thing is truth table. So whereas a truth table is going to define the function of logic gate by providing a concise list of that shows all the output states in a tabular form. This is a tabular form, truth table. Okay, and then a logic diagram. It's a graphical representation of a logic circuit. Okay, so that shows a wiring, that shows the wiring and connections of each individual logic gate represented by the specific graphical symbols. These are graphical symbols. Okay, sir, explain once again. Yeah, simple. Now, when I say combinational logic circuits, here this combinational logic circuit will be having inputs and output. So what is this combinational logic circuit? This is a circuit, a graphical, or what is that? A graphical representation of logic circuit. This is a graphical representation of Boolean functions. The combinational logic circuits are graphical representation of Boolean functions. Okay, so this consists of three stages, three things. One is Boolean function we require, right? Then we need a truth table to show the states of output, input and output in a tabular form. Truth table, it consists of truth table, and then based upon this expression, we are going to draw a logic diagram. This is must. We require an expression. Based upon expression, we need to write a tabular form to say the state of that expression, and based upon that expression we are going to generate, or we are going to draw a logical diagram, circuit diagram, by using basic building blocks of digital electronics. They are AND gate, OR gate, NOT gate, or NOR gate, and NAND gate. Okay. So where are these combinational logic circuits are used? Say for an example, arithmetic and logical functions. In a calculator, we have a calculators, right? There, addition is there, multiplication is there, um, difference minus is there, product is there, and what different kinds of divide is there, division, right? Percentage is there. In a calculators, we are going to use a combinational logic circuit, right? Like adders, subtractors, comparators, and in data transmissions like a multiplexer, demultiplexer, encoders and decoders, like for an example, modem, right? Modulator and demodulator, where encoding and decoding is being done, signal encoding, signal decoding. Multiplexers, demultiplexers, like for an example, a TV antenna, right? Where multiplexers are used. A number of channels we are getting, and those channels multiplexed in one source and demultiplexed in the TV source, right? Data transmission. Then um, code converters. Uh, Code converters like binary, BCD, 7 segment, ASCII characters, right? For an example, if I type A or B in a keyboard, that is going to be converted into ASCII character in a computer, that is by CPU. Then uh, ASCII character, whatever I'm going to give as input from this keyboard is the ASCII character. That ASCII character is being collected, converted into binary number system, and then that binary number system is again converted back to ASCII number system, and then it is displayed on the monitor screen. Okay, that is about a classification. I think this is main important again. After this, after the next class, we will start module 2, because this is essential. If you don't know these all things, then it is hardly it is very heavy to understand the module 2. Okay, I think the session is coming to end now. We'll stop here. We'll continue in the next class. If you have any doubts, you can personally message me and you can ask anything. Okay, right. Shall we end the session?